We'll be talking about fast and error prediction with no statistical trade-offs.
Thank you. Hi everyone, thanks for being here. So I'll talk about the fast nearest neighbor prediction. Let me adjust this. Sorry. And the question is whether we can do fast nearest neighbor prediction without trading off the statistical accuracy. So here's just basic vanilla nearest neighbor prediction. We have a query point X and the nearest neighbors of it. And usually, let's first take the simple regression setup. In the regression setting, okay, we have n data points, IID, and then y is assumed to be in R. And then the nearest neighbor regressor is just the average of the y values of the nearest neighbors of X. So as simple as that. In the case of classification, y is, let's say y is just two labels, 0 or 1. And then the nearest neighbor classifier now is just the majority of the labels of the nearest neighbors. The interesting thing is that we can reduce it quickly, simply to regression. Take the regressor, which is the average, and just threshold it. So, but this allows us to analyze the risk of the classifier just through the risk of the regressor. So that's the main reason why I'm putting this on the slide. So the prediction time. We all know by now that there are tons of fast nearest neighbor search algorithms. So the question for me is, let's imagine that we use a fast nearest neighbor search algorithm. What's the best we could do? And here, the best we could do would be at least order k, the number of nearest neighbors that that we need to return. Right. So no matter which fast nearest neighbor search algorithm you use, it will be at least order k. The thing is that usually we think of k as very small. We think of k as 5 or 10 and such. But however, for good prediction, we have to think of k as very large, as potentially very large, growing with the sample size. So think of k in the thousands, and then imagine another 1,000 query points. Right? So we all of a sudden have an expensive, potentially expensive prediction. So theoretically, the optimal k turns out to be at least a root of n. So
I just wonder about this, the need for large k. I mean, it's not clear. I mean, sure. I mean, we know that the theorem that if k goes to infinity and number of samples go to infinity, then you converge. But in reality, why do you need large k? I mean,
so I'll show experiments. It will not just be theory. I'll show experiments where you can compare using very few k to using much larger k. And you'll see that the accuracy can be dramatically better. And so if you want to have the best possible accuracy, you will need potentially to have a fairly large k. So that's the key point I'm making here. So, so now I'll just say theoretically why. So the statistical performance of KNN usually, let's just consider the case again of regression. Assume that the dimension of X is little d. And little d here could be either the ambient dimension of the space or the metric dimension. So it could be if X were lying on a manifold, it could be the dimension of the manifold rather than the ambient dimension. For much of what I'll talk about, I'm assuming a generic metric. It's not necessarily a Euclidean metric. So now suppose this is just a classical assumption. Suppose that F is actually Lipschitz. So essentially we don't want the y values to change too fast in small neighborhoods. Then the error of Fk, of the nearest neighbor predictor, can be decomposed into two terms, a variance term, 1 over k, and a bias term of this form. Right. The variance term is intuitive. You are just averaging k neighbors, so the variance will be about 1 over k. And this, if you were to minimize this, this is minimized at k at a root of n. Okay. And so in the end, that sort of means that we just cannot do much better than this root of n. At least that's what this seems to be saying. If I want to have the best possible error for regression, and then you have the same story for classification. You can do a similar bias variance decomposition and see that you require about the same sort of k. So for optimal accuracy, we won't predict. We'll need prediction time to be about this much, irrespective of the fast proximity search algorithm used. So that's a key point I would like to keep emphasizing, irrespective of the fast nearest neighbor search procedure. So our goal is this: we want to be able to get the optimal accuracy, yet in prediction time order log n. So reduce it dramatically to about order log n. Why? Because for instance, for one nearest neighbor prediction, we know that we can do it in about order log n if the data is properly structured. So for instance, it has finite doubling dimension and such things. So we know we can do it in approximate order log n. And so the hope here is, can I do the same thing, but while allowing essentially k to be of this order? Okay, so I guess I hope that is pretty clear. Okay, I'll go back here. And this is for me not just a theoretical thing. I want to be able to give these guarantees. And at the same time, I want the algorithm to work. So it's really both. So the fast prediction with no trade-off, how are we going to achieve this? Just using very simple ideas that are there amongst a lot of the heuristics that people use in practice. So reduce the data quantization or subsampling. So reduce the data set. And then, however, while you reduce the data set, you can imagine right away that your variance, the variance of the predictor goes up. So we'll then do some simple variance correction. And it turns out it's actually so simple, the variance correction that we will apply is actually so simple, but works. And so we'll do some simple variance correction and then show that, okay, now we can do this thing in time log n and yet get exactly the optimal accuracy. The optimal accuracy in terms of the original sample size, not in terms of the reduced sample size. So we'll consider common nearest neighbor approaches, epsilon nearest neighbor, which could also be called kernel regression or kernel classification. Epsilon nearest neighbor, just use all the samples that are epsilon close to the query points, or k nearest neighbor, use the k closest samples. Right.
Sorry, I'm going to ask a very stupid question, but so here D, I should think of D as like a small constant and N big, but not like very
D is fixed, D is fixed. So we're not in the classical high dimensional setting where D is changing.
Yeah, because otherwise things are actually fine. If D is greater than log n, for example, things are actually pretty good for us.
This n to the 1 over D.
Yeah.
Yeah, it's just
okay.
Low dimension.
No, but this is the intrinsic dimension of the data. It's not the
ambient dimension necessarily, yeah. So think of D as the metric dimension, the dimension of the metric space. So the outline of the talk, first I'll talk about data quantization, nearest neighbor and data quantization, how we do this with data quantization, then how we do this with subsampling. And it will turn out that we actually, for data quantization, we have to restrict ourselves to epsilon nearest neighbors. And then for subsampling, we actually could do, we'll talk mostly about k nearest neighbor for subsampling. So quantization. So data quantization, we just want to reduce the data in some sense using quantizers. And the quantizers, for simplicity here, I'll assume that these are points that are picked within the original data. And these are the quantization points. And then we assign the original data to these quantization points. For a query X, once we get a query X, we just pick the quantizers, the quantization points that are closest to the query. And this can be picked in so many ways, either pick the k closest queues or pick all the queues that are in some ball around the query point. So the main issues here are, so a lot of there are tons of heuristics of this type. The main issues are which size of, what is the quantization size to be picked, and how do you actually choose the quantization points, and then how do you use it? So those are the main questions, and all the heuristics vary in the ways they answer these questions. Right? So here are some common heuristics. I'll just call them epsilon and n heuristics. So first, they just give some sort of sense of how you should pick Q. So you pick Q to have small size. You want it to be small so that of course, so that you have fast time. And then you want it to be close to the exercise, so that you maintain, to some extent, the accuracy. Let's say this is the data. Let's imagine that we are in classification, although everything that I'll talk about also holds for regression or classification alike. So YQ, now to for every of the quantization points, you assign a label. And the label you assign is just the average label of the points assigned to it. Okay. Then you do regression or classification. For the regressor here can be viewed simply as the average of the YQs in some ball, in a ball of radius epsilon around X. And then the ensuing classification is just the thresholding of that regressor.
So Q is kind of, it's solving the cluster, the k-means clustering, right? Optimal Q.
It could be.
A lot of time.
Sorry?
It may require a lot of
picking the optimal Q might require a lot of time. So here I'll just make a key point. What I'm caring about is the prediction time, not the, yeah. So, so here are the simple heuristics. The heuristics are fairly simple, and we'll make a few quick changes to the heuristics here. And so the first change is the following. Pick Q as an alpha times epsilon packing and an alpha times epsilon cover of the data. So essentially alpha times epsilon net of the data. Here I'm assuming that alpha is between 0 and 1. Okay. And what this does, this simple change, what this does is it ties the choice of quantization to the epsilon that I'm using for the classification or the regression. And so it removes all the knobs. It removes a lot of the knobs. You just now have a single parameter to choose. Think of alpha as something fixed. I just have to choose epsilon. So in a lot of these things, one thing that I feel like is not discussed enough is that the parameter epsilon need to be chosen. So now we tie all this together. And then the next thing we do is rather than the average of the YQs, we'll just use a weighted average. And this is a step that allows us to maintain the original variance in some sense. Okay. So, and I'll give some quick intuition as to why this thing works. So the intuition is we are going to try to relate FQ, so defined, based on the quantizer Q, to epsilon and n, I'm going to call it F epsilon, to epsilon and n on the n samples. Okay. How you actually build that epsilon net, there is tons of ways of building epsilon net. So you can do it, for instance, through farthest first traversal. So first, again, let's go back to these conditions here. Pick Q as an alpha times epsilon net. The first part is important in the following sense. Here, first, I'm going to suppose that X row, the metric space, has doubling dimension D. And all I mean by that is that the covering numbers, let's say alpha epsilon covering number of any ball behaves like alpha minus D. Okay. So that's all that is meant. And so covering numbers can be related to packing numbers. And so that means right away that the number of points that fall in this ball is bounded and becomes sort of a constant. It's bounded by this intrinsic dimension. Intuitively, the farther I force the points to be, there will be so few points in here.
So another thing, the intrinsic dimension is defined as the limit, but here you have a fixed sample. So I don't know how relevant is the limit as alpha goes to 0.
That's a good point, but for the sake of analysis, I'm using the limit as alpha goes to 0. It at least bounds also the behavior on the sample. It's the behavior on the entire space bounds the behavior on the sample. So, so that's the first thing. That going back to that, there are very few points in here, And since there are very few points in here, we can see right away that now I can have fast prediction because the fast nearest neighbor search just has to return the number of points in here. So that gets the fast prediction part. So now the statistical accuracy part will be obtained by relating FQ to F epsilon, and by when I say F epsilon to F order of epsilon. Okay. So now the covering part tells me this, that the relevant xi's, and what I mean by relevant xi's, the xi's that are contributing to the estimates are very close, must be very close to x. They must be at most 2 epsilon away from x, since the q's are epsilon away and they are an epsilon cover. So what that also means, the distance from the query x to the points contributing affect the bias of the estimator. That's what controls the bias of the estimator. What that means is that the bias of this estimator will not be much worse. Sorry, there should be a 2 here. Will not be much worse than the bias of F2 epsilon. So that relates the bias to the bias of this estimator. So next thing is the variance. So as long as we can get the bias and the variance to be nearly the same as that of F epsilon, we are done. So next thing is the variance. FQ now is this weighted average of the YQs. Remember that the YQs themselves are nothing more but the average of the Ys assigned to the Qs, right? So literally all we are doing here is taking the average, rather than taking the average of the Y values in this ball, we are taking the average of these points, of the Y values of these points. And therefore, the variance of it would be about 1 over the number of points that were contributing to the estimate. As opposed to 1 over mean NQ. NQ here is just the number of points assigned to every Q, rather than 1 over mean of Q, which would have been what the best we could show for if we just use the average. So now, what's left here is to show that 1 over sum NQ is actually not too small. That sum NQ is actually not too small. Okay. So the number of points that contributed to the estimate cannot be too small. So the intuition is actually simple. You argue that sum NQ must be at least larger than the number of points that fall in a smaller ball. Why? Because for all the points, all the original data points that were in this ball, their quantizer must have been in this bigger ball. So therefore, at the very least, sum NQ is greater than this. And what that also means is that the variance of FQ cannot be much worse than the variance of the epsilon and n that would have been defined on this smaller ball. I hope that's how it makes sense. So now, it's not quite the variance and bias of F epsilon, but it's the variance of F2 epsilon. And it's the bias of F2 epsilon and the variance of this other thing. And you can show that those are very close to the bias and variance of F epsilon. Okay. And that gives you that you essentially are getting a rate that is very similar to the rate of the original epsilon and n on all the n samples. So the guarantees are as follows. Assume a fast range search procedure, black box fast range search procedure. For an appropriate choice of epsilon, first, we have that FQ or HQ, whether we're doing regression or classification, can be computed in time order log n plus alpha minus t. The order log n is the time to get to a neighborhood of to find a Q that is close to X, and then find all the Qs that are in the ball afterwards. And in fact, what you have here is sort of the aspect ratio of the quantization set. And that aspect ratio can be shown to be of the right order since the quantizers are far from each other. The excess risk now of FQ or HQ is of optimal order. So that's just from all the intuition I gave a second ago. So here is how it works. Okay, so at least we got the guarantees that we want. And here is how it works in practice. So we tried it on a lot of different data sets. And for varying values of alpha, the quantization parameter. And here is how much of the original accuracy is maintained. The accuracy with respect to, how do you call that, with respect to the vanilla epsilon and n is maintained. And then here in the second part is the speed up in time, in prediction time. And so we see that the accuracy for various values of alpha, we have nearly the same accuracy as before, but with very potentially large speed up. One thing I have to say here quickly is that both the epsilon and n and the quantization use fast range search procedures. And so we are comparing quantization with fast range search with no quantization and fast range search. And yet you have all this speed up. And so just going back a bit to Shai's question, so the choice of K is not is actually not just a theoretical thing in that sense. Right. Another thing that we notice here quickly is that as alpha increases, as the quantization parameter increases, alpha acts sort of as a knob between a trade-off knob between time and accuracy. So as alpha increases, the error goes up, but the prediction time goes down, right? Because you just have fewer and fewer points in the ball. Okay. What I'm comparing here also, another thing that I want to say is that these are cross-validated. So this is under the best choice of epsilon for the vanilla procedure and under the best choice of epsilon for the quantization procedure. What was that question?
I wanted to ask you about the choice of epsilon.
Okay, yeah. Under the best choice through cross-validation for both. And another thing is that the errors or the result that I had earlier when I said for a good choice of epsilon, that choice of epsilon could actually be made through cross-validation. You still have the same result. So the main downside, however, of quantization is that computing Q can be order n squared in the worst case. And so this could be too much. And so one might start thinking about, rather than quantization, subsampling, which can be done so much faster. Also, another problem with the quantization is that I focused on epsilon and n for a particular reason. It's sort of unclear how to choose a quantization with with the properties I wanted, to choose a quantization for k and n rather than for epsilon and n. Because the way we tie the quantization to the algorithm is using the fact that the neighborhood sizes are fixed. But for k and n, the neighborhood sizes are changing over space. So it's sort of harder to know how to choose the quantization there. I tried for some time, then I decided just to go to subsampling. So nearest neighbor and subsampling. Any question here?
So the quantization time is actually n times the size of Q, right?
Sorry.
If the time for quantization is n times the size of Q, is that right? If you're doing, say, a furthest first.
Yeah. So yeah, it doesn't have to be exactly n squared, but it's still large. That's the point. And any other question? So nearest neighbor and subsampling. So I'll talk quickly about subsampling. So what we'll do here is here it's not just heuristics actually. There are tons of very nice theoretical results on subsampling as it has to do with nearest neighbor. In fact, there is a whole literature on the so-called boosted 1NNs. And so I'll explain it in a second. So here, again, I have the original data, and then I subsample a few points. And that's the way I reduce the data. So, however, I'm going to use a bag of so many subsamples. So, big N subsamples ST of size little m, much smaller than n. Okay, so I have many of these subsamples, and then the idea here is that I'm going to do one nearest neighbor on each of the subsamples, and I'm going to do the one nearest neighbor in parallel. So imagine that I have n different computers and each subsample sitting on a different computer. So that's a bit of a downside because I need to use this many more resources in order to maintain time or to get fast time. But that's sort of the idea, that it can be done in parallel. So now so this is the query X. For every subsample, I compute the nearest neighbor, the one nearest neighbor estimate for classification estimate for each subsample. And then all I do is I take the majority YT over all the subsamples. Okay, so that's why it's called bagging of one NNs. I hope the procedure is clear. I just take a bunch of subsample, one nearest neighbor on each subsample, and then average the one nearest neighbor values. So now there are these two parameters, n and little m, and how do you choose them? That's really the big problem in practice. How do you choose these two parameters? And Bio and Samworth, Beard et al. And Samworth had a lot of really nice analysis of this. How do you choose n and m? And obviously, large n would reduce variance. You want a fairly large n to reduce variance. And then, interesting, there is a trade-off on little m, on the subsample size. And small m means richer subsamples. You can imagine that if m, the subsample size, is too large, then you don't have much, they all look the same. Right. They all look the same. The variance is very small, but they all look the same. And so you're not really doing much. So little m gives you something richer, but has more variance. And so you don't want the m to be too small nor too large. So the optimal choice, they sort of understood, under certain conditions, they can show that the optimal choice is of this form, of little m is of this form. It's a root of n, which is good because you can let the ratio m over n go to 0 as the sample size goes to infinity. And the smaller m, the faster you do. So that's a very nice property. So here is how it does. On Miniboon, it does better. So this is 1 and n, and this is k and n under the best choice of k. And subsample size here is 10%. Here it's 75%. And as the subsample size goes up, as the intuition I just gave, the error of the bag NN is not that good. But here the error is much better for something smaller. If you went much below this, the error then starts going up again. So it turns out that, at least in the various experiments we did, that picking the ratio to be about 10% seemed to do fairly well. However, this error is not at all close to the best KNN error. And so the hope for us is, can we get it here? Can we get it down to here? Can we maintain the accuracy? So speed up, in terms of speed up, we have huge speed ups. 2 to 8 times speed ups throughout, depending on which subsample size you are using.
This is uniform subsampling, right?
Sorry?
This is uniform subsampling.
Yeah.
It's not any kind of importance weighted or...
No, it's just uniform. Yeah. So now, can we get the accuracy down to that of KNN? So that's the question. And it turns out that yes, you can get the accuracy down to that of KNN if you allow the number of subsamples to go to infinity. And if I went back here, okay, I just had 10 subsamples, but maybe I could have let it go much larger. But my problem here is that every subsample is on a different machine, and you don't want to have to use so many resources. So the question is, can we get such a high accuracy for small number of subsamples? Right. And yes, you can do it, again, simply by correcting the variance. But now you want to correct the variance in each subsample separately. And in fact, you can just correct the variance of every y. The problem that's happening is that you are using a one nearest neighbor for the estimate on everything, and it has very high variance. So you can correct the variance at that point. And a simple idea to correct the variance at that point is replace the y values by a previous nearest neighbor estimate of that y value. I hope that makes sense. I take my original.
Rather than reading the value, you just estimate it from the points around it.
Yeah, exactly. Rather than just using the Y value, I estimate it from the point around it, but I can do that in pre-processing time. I can do that ahead of time. And so it's a very simple idea, and it also works. So here is what we get right away. This is, again, the bag NN. And by just doing this, we get close to the KNN accuracy while maintaining the time, the speed up. We get close to the KNN accuracy with very few subsamples quickly. So it was interesting to us that such a simple idea just works. And even explaining why it works is, takes a few lines. So the guarantees we have is the following. Now we need to assume a bit more. Suppose that px is doubling, is doubling, so it just bound on the growth of the measure. And that E of y, the regression function, is Lipschitz. So for a good choice of k as a function of n, we have the following. We have a parallel computation time no more than that of 1NN. So again, we're using a fast 1 nearest neighbor search on every one of the computers. And the parallel computation time is no more, there is nothing to show there. It's no more than that of 1NN. It actually could be better because we're using a subsample. The excess error is at most the optimal excess error in terms of k, plus this quantity, m to the power of m minus 1 over d, plus this quantity. So because we can express the error in terms of both n and the subsample size, we can also find what the optimal subsample size is. And just as in the earlier result of BO and such, we can show that you can let the ratio of subsample size to sample size go to, go to 0. Go to 0. Yeah.
But does the optimal m remain the same, or is it now smaller once you've made the corrections to the y's?
It remains the same. The order of it remains the same. I was surprised by that, but the order of it remains the same. Actually, in hindsight, the reason why, the way they prove, the way they obtain earlier the optimal m is by relating the bagging of 1NS to KNN. They related it to the order, to the risk of KNN. And the idea, actually, offline, I could explain how the relation is done. It's actually really neat. So you have this. And, but going back to your question, I'll say something more. I'm writing opt here because in a lot of those work, they don't consider, for instance, the margin of the classifier and such things. And so here in this work, we consider also the margin. And once you consider the margin, then the optimal m would depend also on the margin parameters.
What is k here? I'm missing something.
K was just for the denoising phase. So how do we correct variance? We just denoise. Right? We denoise by a k nearest neighbor.
And how do you choose k then?
And so you choose k again by cross-validation.
But that's pre-processing.
That's pre-processing, yeah.
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 Okay.
And so the intuition is simple. Suppose that big N, the number of subsamples is 1. Suppose the number of subsamples is 1. Let S of x be the nearest neighbor of x in the subsample S. There is a single subsample here. Then the estimate at x is just the estimate, is just the k nearest neighbor estimate of S at S of x, right? The next thing is that we know that the k nearest neighbor estimate at S of x is close to the base. Close to the base up to optimal error for a good choice of k. Because we have Lipschitzness, we also know that the base at S is also close to, at S of x is also close to the base at x, plus essentially the distance between x and S of x. And the distance between x and S of x is essentially bounded by this, by n minus 1 over d. So that's the gist of the...
Factor of like, I mean, there's a factor depending on k between opt and
Yeah. So here, what I mean by the squiggle is is a rate depending on k.
okay, multiplicative.
Yeah. Sorry?
It's multiplicative.
Not necessarily. It's a rate depending on k. I mean, if I I just take the difference and take a bound on the difference, and if the bound on the difference would be like 1 over k plus something. All right. So that's the key idea. Is that okay? Suppose that you have a single subsample, you can do this relation. Now you have multiple subsamples, so the variance can only go down. The good thing here is that there is already a variance correction here. So you know that the variance of the original KNN is good, but it's the variance at S of x. Now you have this additional bias term, but everything then works out. So that's the key idea. So that's essentially much of what I'd like to talk about. So the key point is that it is possible to get the original accuracy of the vanilla procedure, so no trade-off, nearly no trade-off, not only theoretically but also experimentally, also in practice, in the time of 1NN, or in the time of fast 1NN, or even potentially faster. So there are many open questions. One is how do you integrate all the data structures? So there is a bit of abuse in what we're doing here. For instance, in the quantization case, we construct this quantization, and then we use a black box fast nearest neighbor search, which also often works by constructing other quantizations, and so maybe we want to integrate all of this. Another point is that the quantization or the subsampling are not taking y into account. Right? You can imagine that if there is some region where y does not change much, then maybe I don't need so many quantizers in that region. So maybe we can design a better quantization by taking y into account, or design a better subsampling distribution by taking y properly into account.
Assuming that the Lipschitz is changing over different...
Yeah, that's sort of what I'm assuming, which is often the case, and you might be able to detect it in data by taking y into account. So then there is simply the question also of we can ask the same questions for related methods such as kernelized support vector machines. You have the same sort of problem that if you use a kernel version of support vector machines, you end up using, the vanilla version is too expensive. You end up using all the sample points, right? And even if you are doing fast approximations to the kernel and such things. And so can we also here not have to have a trade-off? There's tons of nice work on this problem, but that all shows some sort of trade-off between time and accuracy. And the question is, can we actually maintain the accuracy and get a very nice trade-off, maybe through subsampling or quantization and such. So that'll be it. Thank you.
Any more questions? Yes.
So just a question about the correction for one nearest neighbor, where you replace the label of every point by the majority or average of its k nearest neighbors. So one nearest neighbor by itself is not consistent, but suppose you were to just correct all the labels in this way and then apply one nearest neighbor, would that be consistent?
Yeah, I suspect so. Because, I mean, essentially that's what we have here. We have consistency, not only consistency, we have the rates of the original KNN, right?
But this is consistency for a bagged version of those, correct?
Oh, yeah, okay. Yeah, we'll have consistency for the non-bagged version because, in fact, what we showed is that even for a single subsample, just doing this correction. But here is a point, though. Here is a big point. The assumption that the distribution is doubling is very important here. The distribution being doubling sort of means that there is a uniform coverage throughout. And the uniform coverage becomes essential because what you are replacing your estimate by the nearest neighbor estimate, and you want the nearest neighbor not to be so far, and so coverage becomes important in here. And so for general distributions, I cannot say yes right away, but if you have benign distributions, yeah.
Any more questions? Okay, if not, then let's thank the speaker again. Just two announcements. First of all, you do